Hello everyone, hope you are doing well. Welcome to the online platform Civil Techno Bricks. Guys, here we will tune for the instantaneous decoding of the conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts based on the Cloud GIS and software architecture. Cloud GIS is a system where GIS data and services are hosted on cloud platforms, which are accessed with reference to the internet. The main objective is to enable the remote access, data sharing, and real time collaborations, distributing the spatial intelligence from client server models to any type of smart city applications, which is the most important role in the Cloud GIS. Cloud GIS works by storing the spatial data on cloud servers and delivering that GIS services through web applications. The characteristics includes the scalability, flexibility, cost effectiveness, and multi-user access. The users or the people who are dependent on that GIS cloud, they can perform mapping, analysis and data updates without installing heavy softwares. In civil engineering domain, that is used for smart city planning, disaster management and real-time project modeling. So GIS software architecture, which defines the structure and components of a GIS system. The main objective for that software architecture is to ensure efficient data process, storage and visualization, which works through different layers such as data layer, application layer and user interface. The common architectures for that software may include that desktop GIS, client server GIS and web based GIS. So we can use that GIS for different procedure and domains. Today we will see that the cloud, which is a huge amount of space where used for storage of data or use that storage for the sake of development by the engineers to access, analyze and share the project data from anywhere in the world. That cloud GIS and software architecture is the future of collaborative engineering. What are the key components of cloud GIS? Basically, the cloud computing process stores and compute services over the internet. The main objective is we have to access the remote data and we have to scale that data. It works through the servers which are hosted or which are operated on cloud performance or cloud platforms. That types are software as a service, platform as a service, infrastructure as a service. These type of platforms are used in civil engineering for data sharing, project collaboration and real-time monitoring. The cloud GIS ecosystem consists three main components: infrastructure component, platform component and software component. Infrastructure refers to the virtual servers and storage provided by companies like Amazon, AWS or Microsoft Azure. The platform provides the environmental for developers to build custom engineering applications. Software as a service is what most engineers use, such as ArcGIS software, QGIS software, where GIS tool is used as a access directly through a web browser. Understanding these layers, which helps engineer to manage, choose the right level of control and cost for their specific project needs. Moving towards the evaluation point of architecture, the architectural balance is most important phenomenon where we have to maintain the equilibrium based on the system functions. So these all components be a part of system must be in equilibrium so that the balance will occur. With reference to data, hardware, software and user, just like people, GIS architecture has evolved from standalone desktop system to client server networks, and finally to the cloud. In a desktop environment, all data and processing which is on the one machine. So in client server model, a central server stores the data, but the processing still happens on the user's computer. So two parts: desktop environment for the one machine dependent, client server model which is server dependent. Cloud GIS represents both data storage and heavy computational processing which happen on remote servers accessed via the internet. For civil engineering firms, this means you need not require expensive local hardware to run complex flood simulations or any 3D terrain analysis. So the process started from the data and end up to the user. Data, which is the fuel, that data must be in any type: raster, vector, attribute, spatial. Likewise, some supercomputers or some desktops are the hardwares which are use that data, and softwares, they are the input softwares or the database management system or the relational models or the manipulation system based on some technologies or based on some browsers where people or the decision makers study or use that data, that hardware and that software for the sake of our decision policy. Now, client server model. We studied the relational database model previously. Now we have to study client server model where the separation presents from heavy data processing. Now here two sides, client side is there and one is the server side is there. Client side, which is a presentation, or we can say that the GIS interface, where the desktop provides the n number of visuals from where we can add query or we can generate query or we can process any request. With reference to that request, the whole server, which is based on some activity like cartographic files, some hybrid data model, some attribute tables or information, working on that request and gives the response to that client. The presentation for the client interface provides visualization of tools, map navigation and user interaction through GIS software or web platforms. Civil engineer use this layer of for terrain analysis, infrastructural mapping. Spatial data management, that is the server stores cartographic files, attribute tables, spatial data sets within centralized hybrid models. With reference to request communication, the client sends spatial queries or analysis request to the server. The server processes that request, returns results in real time. This architecture improves speed, accuracy, scalability, and collaborative GIS operations for urban planning, transportation system, and environmental monitoring projects. Point for the GIS point of view, which is a web GIS workflow or nothing but a process of data where the data acquisition, which started pre-processing, then data management, followed by the manipulation analysis, and then product generation. Here, the Cloud GIS follows a systematic workflow starting from data acquisition to product generation. Remote sensing data from satellites, drones, and field observations are collected, processed, and integrated into cloud based GIS platforms for efficient civil engineering analysis and decision making. Pre processing data management within the workflow includes the tasks such as format conversion, age matching, and correction to ensure data consistency. Cloud database management system stores enable centralized management for large spatial datasets, while GIS analysis tools perform geometric operations, terrain modeling, infrastructural analysis. At the end, product generation for civil engineering point of view, the GIS products such as digital maps, thematic layers, soft copy images are generated and shared through web platforms. These outputs support transportation, planning, drainage analysis, smart city development, construction monitoring, environmental assessment with faster accessibility and collaborative cloud-based operations. Point for the data, that is the physics of data transmission. If we have a huge amount of data, we have to store that data with reference to the database management system. We have to relate that data with reference to the relational database management system. We have to use that data for client point of view or server point of view. Then we can use client server model. So n number of models we can attain, or n number of servers we can use for the data processing, pre-processing, or product generation. For the transmission point of view, we have to transmit the data, means we have to generate the procedure for the transmission based on the rate. Then data rate, which is based on the constraints, where massive volumes from high respective sensors, just like hyperspectral sensors, are used based on some constraints which explains the size of data. And that size of data, which is most importantly depend on the constraints of time. That constraints are latency limits with reference to real time processing. So time on the basis of real time scenario. What is the requirement of output? We have the output with reference to the transmission must exceed acquisition speed, means that physics of data transmission is most important, play the role for expanding the acquisition speed or integrating the acquisition speed. Most important point is that scale of storage. The scale of storage is start from bit to byte, then kilobyte, megabyte, gigabyte, terabyte, likewise. So with reference to that, n number of storage which will be scaled with reference to the requirement for the data storage. 12 terabytes of raw data collected in 11 days. 12 terabytes of raw data is collected in 11 days, which is equivalent to 15,000 CD-ROMs. Means if we have to convert the whole stored data with reference to the CD-ROMs, then 12 terabyte data is collected in 11 days. Means data and time which generates the rate of transmission, which gives the scale of storage. What are the advantages for that cloud system, or we can say that cloud GIS system? For cost effectiveness, data integration, accessibility, scalability. So one of the biggest advantage of cloud GIS is a scalability. If a project suddenly expands from a single bridge to an entire highway corridor, the cloud can automatically scale up its storage and processing power to handle that increased load also. So importance of cloud is most important in civil engineering domain. If we add on some activity within the actual process of construction, then that cloud have the capacity to enhance its storage capacity, that is a scalability. It also offers a pay as you go cost model, which is highly beneficial for civil engineering consultancies. Instead of some massive investments in servers, construction firms can pay only for the resources they use during the life cycle of project. With reference to the data integration, linking raster imagery with vector attributes with reference to the database management system, which also integrates the data safety and security. Accessibility point of view, we can say that the spatially reference data available anywhere, everywhere, anytime. So we can use that available spatial data for the our sake of purpose or objective. Most important, that is the security of data and integrity of data. So security and integrity of the data, which is based on the four parts: access control, privacy, reliability, and integrity. What is meant by integrity? Where preventing the numerical rectification errors. What is meant by reliability? Backups against accidental data loss. Data privacy, which is a protecting sensitive attribute tables, and access is the limiting authorization to prevent manipulation. Means for that data security and integrity procedure, the Cloud GIS architecture uses access control mechanism to restrict unauthorized modifications of spatial and attribute data, data integrity and management privacy, which ensures that spatial data sets remain accurate and free from rectification or processing errors when we perform the GIS operations on it. At the same time, data privacy safeguards sensitive attribute information such as land ownership, demographics, engineering project details within the centralized cloud database. Reliability and backup system in the Cloud GIS maintain regular backups and recovery mechanisms to prevent accidental data loss, which improves continuity in civil engineering projects such as transportation planning, smart city management, disaster monitoring, infrastructural maintenance. What are the applications of Cloud GIS in the smart city? The layered approach to urban management means on the basis of global positioning system GPS, we can mark the coordinates with reference to the geographical information system. We gather the information for that coordinates with reference to the layer structured. We can segregate the whole area or land parcel with reference to the all layers for that entity enclosed in it, just like vegetative material, land parcel, land records, then layouts, watershed management activity, vegetative material, characteristics of soil, terrain analysis, and many more. So land parcels, or for the cadastral mapping point of view, we can study the layout maps. For the zoning and urban planning point of view, or for any density, population density, traffic density point of view, we can use urban planning and densification control. For the utility, just like drinking water purpose or safety sewer lines, utilities, we can use the network modeler. Means for civil engineering point of view, Cloud GIS used to store the huge amount of data with reference to the layered approach, and it will more important for the urban planning and management activity. What is meant by the civil engineering use cases? So civil engineering use cases point of view, there are two images are there. First, terrain modeling. Second one is the disaster management. The first image explains that the actual digital elevation model, which have some elevation with reference to some standing lines and some contours. With reference to that standing lines and contours, we have to mark the ridge lines or the ridge points. At the same time, we have to mark the valley lines. Means the potential route of water flow with reference to the gradient and slope available. Means the slope gradients provides the valley portions where the whole rainfall water will be captured, and with reference to the slope, that whole water may flow from A location to B location. So slope analysis and infrastructural route planning using digital elevation models, which is a terrain modeling, is one of the use case for civil engineering. At the second time, disaster management, which is the post analysis point of view. As event occurred of disaster, then we have to analyze that event based on some floodplains, destroyed bridges, damages, and many more activities. Just like for Sumatra tsunami, disaster management point of view, the civil engineering use cases is that scored floodplain area, destroyed bridge structure. Likewise, activities are identified with reference to GPS and GIS. The whole information will be collected, and with reference to layered structure data, every disaster activity will be segregated with reference to each and every disaster impact, and analysis will be in picture. The four M's in the Cloud GIS. The goal of Cloud GIS, which is based on the measurement, mapping, monitoring, and modeling. Measurement for the remote sensing and survey point of view. Cloud GIS begins with spatial data acquisition from satellites, drones, GPS, field surveys, mapping and monitoring, where collected data is processed into layered digital maps for visualization, while continuous monitoring, time series analysis and change detection of roads, urban growth, flood zones, and construction activities in real time. Modeling and decision support, where Cloud GIS integrates simulation, predictive modeling to support engineering decision making procedure, which helps civil engineers to analyze futuristic scenarios, optimize infrastructural development, and improve resource management through scalable cloud based software architecture. Stay tuned, guys. Happy learning.